Hello and welcome back to Calculus 3, part 2 of 13.1 on double integrals in rectangular region. So we talked about the cookie cutter, we talked about the shape we have, which is a box, flat sides everywhere except on top. That's governed by some function. So the top is given by some function z equals f of xy. And what I tried to do, and then the network and everything exploded, is make a cutout in a domain and bring it all the way up to the surface, which creates what we call a representative French fry. This representative French fry has delta x and delta y in its base, which would immediately upgrade our integral to the double integral, because now you see that your integral has to have dx and dy and then the function, right? So we should have two squiggly lines for it, two integral lines, and then one belongs to dx, one belongs to dy. So that's why we call it a double integral. So what I have here is that I am going to have a function of xy, and that function is going to be multiplied by delta x and delta y, and we're going to add all of those. So this over here is the volume of a single French fry, right? Because I have the width on both sides of the French fry, and then its height is given by the function. So I have the x times y times z, well, dx times dy times z, to give me a single French fry. Then we have over here again, so this is single. Then I have many, because we go up to n. And then finally, limit to send n to infinity for all. It's exactly the same thing like in Calculus 1, except you are adding another layer of integration on top of everything. And now we call that double integral. So this Calculus 1 Riemann sum is now written this way: double integral over rectangular region R for function fxy, and we say dA, I'll explain that as well, is equal by, now this is the definition, limit where delta goes to 0. What delta? Well, delta x and delta y, they go to 0 for summation 1 to n of f of, now they're using xk and yk, so that means k goes to 1, or k starts at 1, delta a k. So this is the official definition. And again, single French fry, many French fries, all of the French fries for exact. That's what it is. Now, what does this mean? Well, first off, our dA is either dx dy or dA is dy dx. You can have them in any of these two orders, right? You can have x first and y second and so on. Now that will give us the integral that will look like this: double integral of, let's say, x minus y dy dx, and we have to provide limits because the rectangular region has to be finite in order to be rectangular, right? So we must have a, b, c, d around. So I'll put some, I don't know, 0 to 2 and 4 to 6. It doesn't matter. We'll put some numbers here. So this is the example of a double integral that goes, that has this. Now, if I want to draw this rectangular region, I can simply represent this here. I have, now this is what we are learning now. The inner part is a unit, and then the outer part belongs to each other. So you see that x is 4 to 6. So you go on your drawing, 2, 3, 4, 5, 6. You go to your drawing and you put vertical lines at 4 and at 6. And then y, dy, is between 0 and 2. So 0 and 2. And we are integrating over region R, in this case, which is a square. It's a 2 by 2 square, but it's located at this between 4 and 6, right, on x-axis. So now your shape is on top of this region R. That's where the shape is, on top of that region R. And the top of the shape is going to be given by the plane x minus y. You can go ahead in Mathematica and graph x minus y to see what it looks like. How do we solve double integrals, triple integrals, quadruple integrals? If you have 15 integrals, how do you solve them? You do one by one, inside out. That's what you do. So you copy the outer 4 to 6 integral, and now you're integrating the inside in respect to y. Integral of x, well, that's a constant, so it's just xy, right? Minus y squared over 2, and you will compute that 0 to 2, and you still have dx. So please note that all I did is the Calculus 1 problem in orange. And I just copied the second integral at the end. So now I have to compute the inner part at 0 and 2. That's just Calculus 1 again. And then I'll have another Calculus 1 problem to solve. What do you have for double, triple, quadruple integrals? All you have is nested Calc 1s. We don't have any new method to learn. What we are learning now is that your region is rectangular. We are going to connect that knowledge. If you have numbers only in limits, region is rectangular. And this is the part that you are supposed to write on the cover of your notebook. If the double or triple integral or 15 integrals have only numbers as limits, it's a rectangular integral. Region is rectangular region. So we will call them rectangular. There will be a rectangular integral within the polar coordinates, which makes no sense. But as I said, word rectangular is not now only used as a rectangle. It's also associated to the fact that you have numbers around. And to solve any of these integrals, double, triple, whatever you have, you will only focus on the most inner integral and then work your way out. You will always solve Calculus 1 problems. There are no Calc3 integrals. There is a Calc3 setup, but all calculation, entire chapter 13, all of the calculation is a Calc1 after Calc1. I mean, sure, if you get integration by parts or something, then it's a Calc2, but we are not learning new methods of integration. So now, since we are here, I copy the outer integral 4 to 6, and now I plug in 2 for y. I get 2x minus 2. When I plug in 0, everything dies, and I still have dx to work with. The integral of this is x squared minus 2x, computed from 4 to 6. And now it's 36 minus 12 minus 16 plus 8. That's 24 minus 8, which is 16. What have I calculated? Well, I calculated the volume. Volume equals to 16 units cubed. Centimeters, inches cubed, whatever the units were. Why is it a volume? Well, what did I do? I pressed the cookie stencil into the dough. You have a cookie. This cookie, in this case, has a square base and some wavy top, which is given by the function x minus y. So it's going to be, you know, some trapezoidal cookie or whatever. And its volume is 16 units cubed. Why is it volume? Well, we dealt with 3 dimensions. I have this situation. Dimension number 1, dimension number 2, dimension number 3. It must give me the volume as the answer. So these are 3 dimensions. So it better give me the volume at the end. Now, do you see how you can use the double integral to also calculate the area? Just kick the function out, right? If you kick the function out, all you have is dy and dx. So say you are tutoring, you know, 5th grader in their basic formulas or geometry, where they say that the area of the rectangle is a times b, and the little critter comes up with y. Okay, let's see why, right? So what do you have? It's 3 times 5 rectangle, right? And the good old a times b formula was not enough. So what do? You say, let me put this in the coordinate system, xy, and now set up double integral, not even single integral, double integral, which would be, let's say, dx dy. dy is on the outside. It belongs to the outside integral. Y goes from 0 to 3 on the picture. The inner integral belongs to the inner dx, which goes from 0 to 5. There you go. This is the double integral set up to compute the area of this rectangle. Right? Why simple if you can complicate things? Compute the inner integral. So copy 0 to 3 integral on the outside. What's the integral of 1? Variable. And what's the variable? X, because we have, so x calculated 0 to 5, and we have dy on the outer side. So when I calculate inside, I have 5 minus 0, which is just 5, dy. What's the integral of 5 dy? 5y computed from 0 to 3, which is 15 minus 0, which is 15. That's y. Now, can you all spot that you could have set this up as a Calculus 1 problem right there? Right? That's a Calculus 1 setup right there. So, good. So now what we're learning? We are learning, and this is some of the stuff for your notebook cover if you want to sort these things out. Volume is going to be the double integral of a function, and then we put dA, where dA is dx dy or dy dx, or area, just double integral dA, no function. No function. And then we also say that the double integral with a, b, c, and d, numbers only, is a rectangular region. Rectangular region integral. So we're starting to categorize this. What's the next lecture? These numbers become functions. And then you are going to have a parabola in domain and another parabola in the domain, creating like a, you know, if you put the football and shadow of the football, so that will be the region. Vertical walls up, some kind of top. Welcome to general regions, right? So that's the next step. And in that case, the CD part become those two parabolas. So we are going to upgrade this. This is just the first step. To calculate double, and I'll put here or triple integrals work from inside out, and be careful with variables. The inside is either dx, that means x is the variable and the y is constant, or the inside could be dy, which means y is a variable and x is a constant. Double integral of e to the xy dy dx from 0 to 1 and 1 to ln 5, whatever, doesn't matter. I start by focusing on the inner integral only, completely disregarding that dx exists at all. As soon as I zoom in that the variable is y, x becomes a constant. So I have to fix this x e to the xy. This should help. So now what do? I go and I compute the inner integral. So copy the 1 to ln 5 on the outside, and the inside x is a constant, so I copy x. The integral of e to the xy is e to the xy over x, computed from 0 to 1, and I still have dx. If you recall your Calculus 1, when you have integral of e to the ax dx, the answer is e to the ax over a plus c. Do we all remember that from Calculus 1? It's the u sub part that you memorized. So the constant in front of the variable goes in denominator, right? Well, now your variable is y, which makes x a constant, and this x a constant as well. So you copy the constant x, which is this one, but when you take the integral here, the constant that was a before is now x, and it goes down. And now they cancel. So these guys will cancel. I don't need this anymore. And we can compute the inner integral as e to the xy computed from 0 to 1 dx. So now that's wise. Usually where you mess up on exams is you kind of lose the track which variable was your main variable. This calculation here has x and y in it. These limits belong to y because you integrated out y, so you better be plugging these into y. Another thing that is a quick confirmation is you haven't done x yet, so don't plug them in x. You haven't done x yet. X is to be done. These are the limits for x because the outer integral belongs to the outer variable. So the story of this dx and dy now is becoming crucial, right, for your survival and navigating. What's coming up in 13.4? dx, dy, dz, right? So you have to keep track of that. You have to be mentally present, right? No music with homework and stuff. You have to be mentally present when you do these things. So 1 to ln 5, and we plug in 1. So that's just going to be e to the x, minus, when you plug in 0, e to the 0 is 1. That's another unfortunate thing from Calc 1. Oh, it's 0, so it just drops off. No. E to the 0 is 1. Cosine of 0 is 1. So there are certain functions that do not go away when you plug in 0. All the polynomials go away when you plug in 0, sure. But not exponential or cosine function or secant, right? So now I have to solve another problem. This is now pure Calc 1. Integral of e to the x is e to the x minus x computed from 1 to ln 5. So we have e to the ln 5 minus ln 5 minus e to the 1 plus 1. If you use the formula, it turns into plus, right? And now you have 5 minus ln 5 minus e plus 1 for a total of 6 minus ln 5 minus e. And there you have it. So this is the exact answer. Yeah, you can go and get the decimals, no one cares. I mean, people will care when you do your engineering courses, no one cares math. Right, exact answer is perfect. No need for calculator. So now you see entire problem. I have integral. The order is dy dx. The inner limits belong to the inner dy. Because the variable on the inner integral is y, I integrate in respect to y. X becomes a constant, so copy x, e to the xy. Now, what would happen with this problem if the first x in front of e was y? What would happen? Yeah, the integral version of product rule, which is called integration by parts. Right? So you would have to do integration by parts if this was y here. So these are the things that you have to be careful about. Now, what if that was actually a y? do I have to go through integration by parts? And the answer is actually no, I don't. Because what I can do is I can switch the order of integration, and then I would still calculate x, and there would be no integration by parts. So switching the order is something that saves your skin in 13.1 for rectangular regions, because switching the order is a joke. But switching the order in general regions, most of the time is more trouble than gain, because you have to do transformations of functions and everything else. And if they have no inverses, you can't even do it. And then 13.3 for polar coordinates input, you can't even do the switch, even if you wanted to. So there's that. You have to be careful about these things. A lot of categorizing in chapter 13. It's very simple, in my opinion, because it's integration, and I always like integration because I can always check by taking the derivative. But you have to categorize these things, you have to practice in order for this to make sense. So changing order of integration, changing order of integration. And I'll write this in blood. In 13.1 only, we can just swap dx and dy, which implies swap limits on integrals. So your integral that was a, b, c, d of a function dy dx is the same as integral c d a b f dx dy. Note that the limits a, b belong to x, and then a, b still belongs to x, and they are on the inner part. You cannot do this anywhere else, this basic swap. Every single other change of variables thing, swap of the order, will trigger a procedure for you to do that. And that is one of the big focus areas in our next lecture. Because, again, computing the integrals is as simple as you compute the limits, you're done, right? So, challenge for general regions will manifest themselves in setting up integrals, number one. And number two, if you have to change order of integration, how do we do that? So those are the challenges. The rest should be walk in a park. So I hope that this lecture made sense. I want also to show from the textbook the French fry idea. You see that you partition your domain, which is rectangular domain, with some delta x, delta y, which gives you partitioning. The more partition, the thinner your French fry, the better approximation of the surface you get. And if you use infinitely many French fry, the top will be smooth and exact, and you will have exact volume of the shape. Also keep in mind that the double integrals can compute volume, can compute area if you kick the functions out. Right? You kick the function out, it becomes just dx times dy, and that's area. So you can actually use double integrals to redo all of your problems from Calc 1, right? But it just adds extra step. So we don't do it, right? We can, we don't do it. These concepts will be revisited in chapter 14 in the Green's theorem, 14.4, when we transform a line integral that takes a page of calculations into a double integral that takes a single line. And the Green's theorem is the learning outcome of the class, so you will all have to have that on your final exam and so on. It will be converting into these integrals to solve this quickly. See you on Wednesday. We are going to move into 13.2 and just keep computing these things. I will do the general regions next time. See ya.